Thank you very much. Thanks to the organizers for inviting me. It was a little bit funny. At some point, I wanted to organize some conference on something related to symmetric tensor categories. I'm like, I have to be the organizer because I've never written a paper about symmetric tensor categories. All mine are non-commutative, but now I have, and so I'm excited to be invited here. Yeah, so I'm going to tell you about the Delannoy category. This is this example that Andrew mentioned right at the end of his talk. And I'm going to tell you a lot about this example. So I'm going to start with some background, just reminding you some stuff from Andrew's talk in a little bit more detail. And then I'm going to tell you a lot about this one example. Maybe I should say papers in this oligomorphic area, there are theory papers like what Nate just talked about. They're kind of two different kinds of example papers. They're example papers that introduce a new group, and then you get some category, and maybe you don't know so much about it. Here, the group is not new. The group is already in Andrew and Nate's, well, it's new in the sense that it's in Andrew and Nate's first paper, but what we do in this paper is say everything there is to say about the representation category. So that's kind of the kind of paper that this is. It's about what is the representation theory of one particular oligomorphic group. Okay, so let me just remind you from the talk this morning, you have some oligomorphic group, you have some measure on G hat set. So Andrew didn't really talk about this, so maybe I'll say one or two words about this. You have some big oligomorphic group G, and then you had all these open subgroups of it. In fitting into this whole theory is not just the G sets for the big group, but also the G sets for each of those open subgroups. And the measure is measuring not just the indices of these subgroups, which you can think of as telling you the sizes of transitive G sets. They also will tell you about the sizes of transitive H sets for any of these open subgroups, okay? So this measure, when I say a measure on G hat sets, I mean it's going to tell you a notion of size, not just for transitive G sets, but for any G set by just adding them up, but not just for G sets, also for H sets for H, some open subgroup of G, okay? So we're going to have some oligomorphic group, some measure on G hat sets. From that, we can get this category of permutation representations, which is not abelian, and then you can get this abelian version of it, either as we saw in the talk this morning, by looking at these smooth models for this algebra AG, or if your measure is particularly nice, something called regular that we saw, then you can cheat. You could just take the Karoubi envelope here and you wouldn't have to do something so difficult. And then you get this abelian category rep G omega. And in this case, where you can take the Karoubi envelope, you just get something semi-simple, okay? And in the example that I'm going to be talking about today, everything is semi-simple. Okay, so the group that we're looking at is this group of order-preserving automorphisms of the real line. It only preserves ordering. It doesn't preserve any kind of addition or multiplication, just order-preserving automorphisms of the real line. Or if you prefer, this is like this issue about do you want to look at the big symmetric group or a smaller symmetric group. If you prefer, you could just look at order-preserving automorphisms of the rational numbers, and this has some nicer model theoretic properties. Okay, that's the group. So I want to tell you what the G hat sets look like. So I'm going to tell you what all the open subgroups look like and what all of the H sets for each of those open subgroups looks like. So every transitive G set looks like Rn, which is unordered distinct n tuples of points in R. So you take n points in R wherever you want. Now, this says unordered in the sense that they are not given an ordering. Of course, they lie on a line. So instead of saying that they're unordered, you could think that they're canonically ordered. They're just ordered by where they are in the line rather than some additional ordering that you put in. Okay, unordered distinct n tuples. The open subgroups look like stabilizers of these kinds of things. So I take a bunch of points in the line, and I'm going to look at the stabilizer of that. What does that look like? Well, this GA, this stabilizer, is all the things that fix this collection of points. And well, that's just a product of a bunch of copies of our group G again for each of those intervals, right? If you're going to preserve the order of the line and you're not going to move around these 3 points, all you do is move around stuff in here in an order preserving way, move around stuff in here in an order preserving way, et cetera. So all the open subgroups just look like a bunch of copies of G again. Okay, any questions about that? All right. Oh, I meant to say I'm a bad mathematician and I'm giving a slide talk instead of a chalk talk like my collaborators. But as penance for my sins, the slides are up on my webpage. If you just Google me, that's the top link on the webpage right now. So if you want to go back and see what's on previous slides, feel free to go there. Okay. Great. So I was just telling you that the open subgroups just look like a product of G's for a bunch of subintervals. And now I want to talk about the transitive G hat sets. Those are the H sets for each of those open subgroups. It's again, just look at n1 ordered points in the first n1 distinct unordered points in the first interval, n2 distinct unordered points in the second interval, et cetera. And that's what all the G hat sets look like. So these are the kinds of things that I want to tell you what their measures are. And so here's some examples of some G hat sets. This is 2 unordered points in 0, 1, you can think of as this triangle missing the edges. You can have things like a closed interval is a union of an open interval and 2 points, and each of these are transitive G hat sets. The points come from, of course, some trivial case on the previous slide. Okay. All right. So the measure, so this theorem was stated already at the end of Andrew's talk. There are exactly 4 measures on G. The one that we'll care about that's really well behaved, which is Euler characteristic. And then some others that are a little bit less well behaved that I won't talk about that come from Euler characteristic on partial compactifications of R. Okay. So let me tell you how you compute this Euler characteristic in some examples. It's slightly different than you're often used to Euler characteristic of like only closed submanifolds, and here they can be open or partially open. And so let me just show you what happens. So here, if I take this triangle that I mentioned before that doesn't contain its edges, this has Euler characteristic 1 because it has no vertices, no edges, and 1 face. Okay. This one you can think of as 2 vertices and 1 edge, so it has Euler characteristic 1. And all of these things will just have Euler characteristic that's -1 to some power. And so all of the generalized indices of anything are always plus or minus 1. And since this number is never 0, this version of Maschke's theorem that they have tells you that this is going to be a semi-simple category. Okay.
Just a second. So you mentioned some names there, Shapiro and Wheeler.
Oh yeah. This is.
I mean, is it
what version of Euler characteristic are we doing? Apparently appears in So this version of Euler characteristic where you don't have to be like closed submanifolds.
Yeah, but it's very easy to show that there is a measure which is regular, right?
Yeah, no, this is just a source for this slightly weird version of Euler characteristic.
I think not just Euler characteristic, but our theory of integration.
Ah, I see. Maybe I understood. Yeah, so the point is that this measure gives you a notion of integration, and that notion of integration appears in this.
Right, it's called like integration with respect to Euler characteristic.
Yeah. Thanks, that's a good point. Thanks.
But this is often used in geometric representation,
yeah,
right?
Okay.
Also.
Great. So that's how you compute Euler characteristic. And now I want to explain in some examples how you use Euler characteristic to compute some compositions. So we're going to look at maps in the permutation representation category between R, the permutation representation, and R. So by definition, this is supposed to be these G invariant Schwartz functions. So on R cross R, right? It's a matrix from R to R. It's an R cross R. It's a function on R cross R that's supposed to be G invariant. Now, what are the things you can do that are G invariant? Well, there are essentially everything is going to be a sum of three things. This function, which is 1 when the first input is smaller than the second input. This function that's 1 when they're equal, and this function that's 1 when they're ordered the other way. And every G invariant Schwartz function is going to be a sum of these three things. And to compose them, I'm supposed to integrate against Euler characteristic, integrate f of xy with g of yz, and integrate out the y term. Okay, so let me do that in some examples. I want to tell you the composition rules for these three functions. Okay. And everything in this section of the paper, in this section of the talk, is already in their first paper. But okay, so for example, I want to compose 1 of x less than y with 1 of y less than z. I'm integrating over y. So what's going to happen? Well, if x isn't smaller than z, there's going to be no y's that work at all, and so it won't contribute to the answer. And if x is less than z, y can be anything in this open interval. So I have to calculate the measure of that open interval, which is -1. And so I'm going to get -1 anytime x is less than z. Okay, so the composition of this with itself is minus itself. Okay? I could do similar calculations. If I want to take x equal to y and y less than z, well, the only thing that y can be is x, so I just have one point that has measure 1, and that point x is less than z, so I'm going to get 1 of x less than z. And finally, the complicated case, if I want to compose x bigger than y with y less than z, what you get is that y is supposed to be smaller than everything, okay? And so that's always going to be some open interval, right? That it's smaller than both x and z is some open interval that has measure -1. And so I'm going to get -1, but it actually doesn't care what order x and z are in, okay? So you could say that this is just minus the function that's 1 everywhere, or if you want, you could say it's the sum of minus each of those three terms. Right. Does this make sense? You feel like you could compose some matrices? And I'm not going to do the rest of them in detail, but that's the rest of the composition. Okay. So it's not so bad to sit down and start doing these compositions by hand. Great. If you know all of these composition rules, you can look at that. That's some three-dimensional semi-simple algebra. It's just going to be k plus k plus k. I probably should have said at the beginning of the talk what field I'm working over. Everything here works over basically any field. Do we use algebraically closed? I think
over Z, yes. Over Z.
Yeah, it should probably work over Z. I mean, I don't think we set it up to work over Z, but it certainly works over every field. Yeah.
Well, that means it
does something happen in characteristic 2?
No, like the whole theory works parallel in every single characteristic. Yeah.
What do you mean you're not set up to work over Z? I mean,
well, we work with like simple objects and such.
Yeah. What's a pre-Tannakian category over Z? I mean, anyway, it should work over Z, but that's not what we do.
You can define semi-simple category, which means you have some objects, some morphism, some associativity. Yes, you can do over engineering. Categorification of fusion.
Yeah, but like, is it still? Usually, it's not rigid.
No, by definition, it's going to be rigid by definition.
Yeah. Great. So this endomorphism algebra of R is k cubed. The simple, if I want to take the Caribbean envelope, I just need to find the projections in this. There's going to be 3 projections, and that's just an algebra problem. And you can sit down and work out from those compositions what the projections are, and they look like 1. This is a little funny. It's x less than or equal to y and x greater than or equal to y. These 3 things are the ones that are projections, and they give you a decomposition in the Cherebian envelope of R1 into three things: a trivial corresponding to this constant function 1, and then two other things, which I'm going to call L solid dot and L open dot. Okay?
Sorry, no.
Yeah.
What is identity in this home space?
Yeah, the identity is this guy. Yeah, which is pretty easy to see and is clear if you. Yeah, it's very unusual of me to not put the identity in the first column anyway. But yeah. Yeah, and this is always the identity. It's always that all variables are equal to the corresponding variable. Yep. Okay, great. Other questions? Okay, so this is extremely concrete. You could just sit down and check all of this at home. Now, the more elaborate thing here is this description in terms of rep G mu as modules for this algebra AG. Here, instead of R, what you look at is CR, the Schwartz functions on R. And then everything is supposed to actually be concrete now. I no longer am taking some abstract Cherebian envelope. Each of these projectors should project me onto some submodule of CR, and I just want to say what those submodules are. So,
I didn't understand the previous slide. It's related to the question. These are supposed to be primitive idempotent?
Yeah, exactly. Yeah. These are. Yeah, that's why I said. Yeah, I didn't say this word. These are perpendicular projections. Yeah, they're.
But shouldn't they sum up to 1?
Exactly.
And they do.
No. What did I do wrong? Did I miss a minus sign here somewhere? They should sum up to the identity. Is it minus 1x less than or equal to y? Did I miss a minus sign there? No. They should add up to the identity.
Yeah, one of them should be minus.
Yes.
Maybe one.
Minus 1?
Maybe one should be with minus.
Is it minus 1? Maybe that's true.
Oh, yeah.
No, how do you distinguish between x minus?
No, I mean 1 is.
But they should be projections, right?
1.
But the composition as an open interval.
Yeah. I think I missed a minus sign there. If I fix this minus sign, then everything makes sense, right? Yeah. That was a mistake. Yeah, it's that the measure of the point is minus 1. That's exactly right. Yeah. So if you compose 1 with itself, you're going to get 1 plus times the measure of a point, which is a minus 1. And yeah, thanks. Good catch. Other questions? Okay. At least I'm giving a slide talk that I can write on, so when I make a mistake like that, I can fix it. It's still wrong in the website, but okay. So what I wanted to say was each of these projections should project onto some concrete submodule of Schwartz functions on R. And what they are is that one of them is the submodule generated by characteristic functions of half-open intervals where the closed side is on the right. I should be a little bit careful. The open side is allowed to go to infinity, okay? Now, you could take the submodule generated by the characteristic functions of all of these intervals or just one of them, because of course the action of the group will move them around. But that's the right submodule. And what I should do, at some point I had a slide that did this, and I decided I had already had too many calculations in this. But you should go and calculate that if I look at the function on R, which is the characteristic function of some right closed half-open interval, and I act on it by the projections from the previous slide, that one of them should act by the identity and the other two should act by 0. Okay, so that's another little integral calculation that you could do. It's not too bad. Okay, so you have, this is something like left continuous functions of finitary support, something like that, all finite linear combinations of characteristic functions like this. You can then do the ones that are generated by characteristic functions that are half open in the other direction, and then there's the constant functions, and these are your three simple summands of CR. Maybe I'll just say in words, you should be a little bit careful about what generated means here. it's generated under the action of this completed algebra AG. So in particular, you can act by elements of G. That's the easy part. But you can also sort of take integrals of actions of G. So for example, if you only took a finite half open interval, you can actually get the infinite version by acting on it by G to kind of stretch it out and then integrating all of those. So you have to be a little bit careful about what generated means, but yeah. Okay. Any questions about that? So this is this kind of viewpoint that they have that, you know, originally rep-st was not a concrete category. Rep-st was just some, you knew what the Homs were and that's it. And now you can actually realize all of the objects in some concrete way, and here's the concrete way to describe it here. All right. Okay, and the novel properties that were already seen in the first paper is that it doesn't come from groups or supergroups or from Deligne interpolation, that it's semi-simple in all characteristics, and then in characteristic P, it's the first example of a semi-simple pre-Tannakian category that does not have, finite is the wrong word here. What is the word I'm supposed to say?
Exponential. Or moderate.
Moderate, there we go, thanks. Great. All right. So that's the end of the, oh, right, no, and then I wanted to say, that's what we know from their first paper. So the starting point for our paper was just like, what else can you say about this category? What are the simple objects? Not just the simple summands of R, but all the simple objects. What are the fusion rules? What are the branching rules? Right, these are fusion rules, I mean, how do you decompose tensor products? Branching rules, how do you decompose restrictions to the open subgroups? Schur functors, what do Schur functors do on these objects, et cetera. And so the goal of the next section of the talk is to explain our answers to all of these things. I won't prove any of them, but I'll tell you what the answers are. And great. So that's the end of the background. Is there any questions about that, or people feel like you understand what the category is now?
So with these restrictions, so
yeah,
you have many functors from this category to products of category.
Exactly, exactly. There's a restriction from this group to any number of copies of the group, right? From G to the N. In particular, I mean, basically all of it is understood if you just understand restrictions from G to G squared, because then further restrictions are just going to be restricting. Like if I want to restrict from G to G cubed, I just restrict to G squared and then do the same thing in the first coordinate. So basically by branching rules, I mean just what's restriction from G down to G cross G.
But we should keep the same question in mind when we think about any oligomorphic.
Exactly. Yep. Okay.
This one's a little special in that the open subgroups are all just copies of the original.
Yeah.
So like that's
Same.
maybe a little weird.
Yeah, like for ST, for example, like the open subgroups are again STs, but different ones, right? ST minus 1, and here it's a bit of a, I mean, I should say this category is intimately related to S minus 1, and S minus 1 does have a relationship. You have a restriction from S minus 1 to S minus 2, but you can also use that to get a restriction to S minus 1 cross S minus 1. Okay. Great. All right, so now I'm going to move, that's the end of the review and the stuff that was in their original oligomorphic groups paper. Now I'm going to shift to our Delannoy category paper. I will eventually tell you why this is called the Delannoy category. There's sort of a long history in tensor categories of naming categories by the sequences that come up as dimensions of endomorphism algebras or dimensions of invariance, and that's where the name comes from. I'll explain that in part 3. In part 2, I'm just going to tell you everything that we could think to ask about these categories. Okay, so first I want to tell you the simple objects. There's a general approach in tensor categories to finding the simple objects where you kind of maybe take your favorite object, start looking at higher powers of it, and at each step you look at what are the new objects that come up and ignore the old stuff, okay? So we're going to take that same approach. We're going to look at Schwartz functions on Rn, and we're going to focus on just what are the new things, the stuff that first came up at level Rn. So I have a bunch of different maps to see Rn minus 1 coming from the different inclusions of an n minus 1 element set into an n element set. I get a bunch of maps like this, and the new stuff is the stuff that's in the kernel of all of that. So that's where I'm going to focus to try to find, I'm going to try to decompose the new stuff into simple objects. Here's what the answer is. So a weight is going to be a word in these two letters, open and closed. Or I should not call them open and closed. Anyway, black and white. A half-open interval has type filled dot if it's of this form, and it has the other type if it's of this form. Okay, so and we're going to call a tuple of half-open intervals ordered if all of the points in one of the interval are smaller than all the points in the other interval. Now, if one of them is closed and then the next one is open, they can kind of hit there because that is smaller because all the points here are smaller than all the points there. So I can have some ordered collection of a bunch of half-open intervals on the line. I'm going to say it has type a word of the types of each of them. So I take the type of the first half-open interval, type of the second one, et cetera, and that gives me some weight, that is some word in those two things. Okay, that's the baggage that I need to state the theorem. Okay, and then our definition, we're going to let L lambda, lambda is supposed to be a word. Lambda is a word. We're going to let L lambda be the underlying G submodule. This is our notation in the paper for a G module. We're going to take the G submodule of C r to the n generated by the indicator functions of I, which is an ordered tuple of half-open intervals of type lambda. Okay, what does that mean? This is supposed to be a Schwartz function on r to the n. R to the n is n points in the real line coming with their canonical ordering. And all I do is ask, does the first point land in the first interval? Does the second point land in the second interval? Does the third one land in the third interval, et cetera? The answer to all of those questions is yes. Then I get the number 1. And if the answer to any of those questions is no, then I get 0. Okay, so this is some Schwartz function on r to the n. And I take the G submodule generated by those. Again, I think you could take the G submodule generated by all of them or generated by just one of them. You're going to get the same definition. Okay? All right. And then the theorem is, and this is one of the main results from our paper, these are simple objects. In fact, they're absolutely simple. They're absolutely simple. Their endomorphism algebra is just the base field K rather than some extension of K. They're pairwise distinct. That is, one of them is isomorphic to another one if and only if you have the same word. Every simple object is isomorphic to one of these. And this joint kernel is actually it's the sum of the ones of the right length, okay? And in fact, the new stuff is multiplicity free, which makes your life easier, right? So the old stuff may have tons of multiplicities. The new stuff is multiplicity free and consists exactly of one guy for each word of length n. Okay, questions? Yeah.
So, do we have like some sort of ordering on the simples that makes everything like nice?
I mean, there's an ordering in the sense that you can ask what's the first Rn that they appear in. Yeah, I mean, this is.
Oh, but it doesn't work.
I mean, we do, for example, put like a filtration on the Grondy group using this structure and look at the graded, and so this ordering is kind of useful in various ways. Yeah. Okay, so the next thing I want to do is tell you about the fusion rules, how to decompose tensor products. And the fusion rules are given by something called a ruffle product. So there's an existing thing called a shuffle product. And the shuffle product is you take, it's like shuffling two things of cards. So you keep the order of the first set, and you keep the order of the second set, but you can interleave them however you want. And the ruffle product is like that, but you're allowed to have certain kinds of collisions. Okay, so two of the cards could hit each other, and then they have to decide like which card they become, and it gets a little bit more complicated. So the way that this works is you have, so I'm just gonna, rather than trying to write down a general formula, there's a formula in the paper, I just want to explain this in one example. So the shuffles, I could insert this dot first, I could put it second, or I could put it third, and that gives me my 3 shuffles. And if I was doing shuffle product, which is a common thing to do, I would just get those things. Note that shuffle product, you're never going to have any hope of having rigidity, right? Because every object needs to have some dual, and the tensor product of those two things is going to have to have some summand that's 1. 1 corresponds to the empty word, and so we're going to have to be able to allow certain kinds of collisions. And so what happens is, if two things collide and they're the same color, did I make a mistake here? I'm missing a term here, aren't I? If two things of the same color collide, they can be that color. Oh, no, they can just be that color. That's it. That's all I want to say. Yeah? This looks right. Okay. And then, so if two things of the same color collide, they just become one thing. And then if two things of opposite colors collide, they can become either of them or disappear. I think I got that right. So here, this one collides with this. They can collide and become this color, they can collide and become that color, or they can collide and disappear and not be seen at all. Okay. And this last possibility is where you can get the length of the word shrinking, and so you can actually have duals. Okay? And this is how the fusion rules work. Any questions about that? Yeah.
Do you do all the colliding one by one, or?
Yeah, so yeah. So you can have lots of things colliding. So I think the way that we do this, right, is you have a map from, you have like an order, like a shuffle is like a order preserving map from K, set of size K, set of size L to something of size K plus L. But if you have something of size K to something of size L and then just have like a surjective map to any set, that's keeping track of which collisions happen. And then for each collision, you have to look at all the ways that you could resolve that collision, and that's how you define the ruffle product. Yeah. It's in the paper, but it's like, I couldn't fit it on one slide, but you can go and look in the paper if you want to see this written down.
So in particular, the black and the white object are dual.
Yeah, in particular, the black object and the white object are dual. Their tensor product would have like, 2 things of length 2, 2 things of length, it's more complicated. Wait, yeah, 2 things of length 2, and then 2 things of length 1, and then 1 possibility of length 0, and that's how you know that they're dual to each other. Yep. Okay. That's the fusion rules, so that's one of the big results of the paper. We also figure out how to do all the other structures, so we know how to do restriction and induction. The rule for restriction is you cut your word somewhere, but you're allowed to cut it either between letters or at a letter. Okay? And if you cut it at a letter, you just delete that letter. So for example, I could cut before the first letter, and then I just get this. Or sorry, this one, no, that's after the last letter. So if I cut after the last letter, I get, before the cut, I get that, and after the cut, I get the empty set. Okay? So the representation of G cross G that I get is this representation on the first factor of G tensored with that representation on the second factor of G. Okay? If I cut here, that one just disappears, and so I get this tensor trivial. If I cut here, I get this one, etc. Okay, that's the rule. And induction, I insert at the tensor product sign if I want to induce, right? A typical to do induction. I got confused about which one is bigger. Anyway, if I want to do induction from G cross G to G, I start with a representation of G and another representation of G, and what I do is I can insert, I put this word next to that word, and I possibly insert in the middle either one black dot, one white dot, or nothing, okay? So here I inserted just a black dot, here I inserted just a white dot, and here I inserted nothing at all, okay? Questions?
You show these are joined?
Yeah.
You show it by hand or you show it using the theory?
Well, I mean, I think first we do one of them first, then we get the other one from that, right? We do restriction first. What?
I think we do induction first.
Oh, right, we did induction first. Yeah.
Yeah, the nice thing about induction is it's always length 3. We can reduce it simple.
Yeah.
It's particularly accessible.
Yeah. Yeah, so.
But this is a general recipe for oligomorphic categories coming from oligomorphic groups, or you do it for
It's
this
very
case?
special to this.
Okay.
Yeah, I mean, the induction, I mean, the way I think about these, right, is that, I mean, you can actually see what it does on the level of Schwartz functions. If your intervals miss for restriction, if your intervals miss the point that you're cutting at, something very simple happens. And if they hit the point that you're cutting at, then your life is a little bit more confusing. But but the formula for induction is not so bad, but it's very special to this example. Other questions? Whoa, so many questions. All right, yeah.
According to your Fisher rules, if you
Yeah.
restrict your simple objects up to like a number of dots, you should
Yeah.
get a Fisher category, right? Because it's closed. You always get like same number of dots or
It's
less.
closed under tensor product, but not under duals.
Oh.
Yeah.
okay.
So there's like there's a subcategory closed under tensor product that would be all of the dots. Those are basically the wedge powers of L dot, and they behave in a nice way. But then you wouldn't have duals, and to get the duals, as soon as you put in duals, you get the whole structure. Yeah.
Oh.
Yeah.
Is this restriction function, that's the thing you were calling branching rules earlier?
Yeah, exactly. Those are the branching rules.
Is that co-associative or at least coherent?
Yeah, I'll get back to that in a moment. Yep. Yeah.
Yeah, so as I understood, so dual is just recoloring every dot?
Yeah, that's on the next slide. Yeah.
Okay. Will you talk about dimensions of those, or?
Yeah. I forgot to put dimensions, but maybe I will. Yeah. So where should I put dimension? Did I put that? Oh, yeah. No, it's on the next slide. Okay, good. Yeah, all good questions. Okay, so we can say a lot about the Grothendieck ring. Of course, as I said, we told you the fusion rules, so you know the Grothendieck ring, but maybe I will say a few facts about it. Of course, it has basis A lambda. These are just the elements in the Grothendieck group corresponding to L lambda. It actually is a Hopf algebra using restriction as your coproduct. So this is your question about associativity. But as the co-unit, you have to use something that's not very categorical. So this is not some, like the Grothendieck ring is a Hopf algebra, but I'm not claiming that the category is some sort of Hopf category because I don't know how to define a co-unit. The co-unit is given by dimension, and so here's the answer to your question about dimension, right? It's, I think, -1 to the length of lambda. Okay.
But what's the problem with that? Why is this?
Well, for example, the most naive thing to do, like, if I want a categorical Hopf algebra, what should the co-unit be? Maybe a functor to vector spaces, but here it's not even positive, so I don't, maybe it should be graded vector spaces, or say, I just don't know, and we weren't able to come up with anything.
So you don't understand, so you say it has a basis A lambda, and then you say it's polynomial algebra in A lambda?
This is in special A lambdas, yeah. So if you tensor with Q, it actually turns out it's a polynomial algebra in certain A lambdas where there's some combinatorial condition called being a Linden word. And if you restrict to just the Linden words, then the rationalization of the Grothendieck ring is a polynomial ring in those generators. Yeah.
And can you say if you take a non-Linden word, do you know how to, the polynomials that express it in terms of the Linden words, do you know anything about these polynomials?
Maybe the most concise answer is that there's an associated gradient, which is the shuffle algebra. And so the leading order term, you do what you do there, but then there's lower order terms, and I think we don't know.
Like for Deligne category FST, for example, that's an interesting question, and you get some also some polynomials whose I think Nate worked on it as a graduate student, and then Chris Riba actually solved this problem completely, characterizing these polynomials.
Mm-hmm. Yeah, it's an interesting question. Yeah, we did.
So you can write some nice generating function for that.
Yeah, yeah. Yeah, it's a good question. We didn't think about that. Yeah. Just some other things. We can actually, the decomposition of CRN is actually very nice. Oh, I should have said this is lambda with, oh, no, I didn't write it because it disappears for, okay. If lambda has length longer than n, this binomial coefficient will vanish, and so that's why I didn't write a condition. Anyway. So what you get is that, now I'm unhappy. Oh no, this is a direct sum power, not a tensor power, so it's fine. Okay, so the number of copies of L lambda inside Rn is n, choose the length of lambda. Okay, that's particularly nice. You can see this, maybe one way to see this is actually Rn is induction of the trivial from the open subgroup coming from endpoints. So this is actually some fancy version of the induction formula. It's just inducing over and over and over again. Yeah, and here was Sasha's question about the duals. You just switch the letters. There are a couple different involutions here. So there's the dual involution. There's also an involution coming from switching the order of the line. The one coming from switching the order of the line is a little bit more complicated because each of your open interval, not only have the open interval switched direction, but the order of them has switched direction. And so you have to do something like switch the order and switch all the letters. And of course, there's also an involution where you just switch the order. So it's very easy to get confused about the different involutions. I think I got the right one here. You just switch all the letters. Okay. And I go to 1220, is that right? Yeah, great. Okay, so we can also say a lot about the Schur functors. So there's something called Adams operations. Adams operations are the thing that for a group replace a character with the function that's character of g to the n. And so all of these formulas for like, what is the character of a wedge power are formulas for the wedge power in terms of these Adams operators on the Grothendieck ring. So the interesting thing is that Adams operations are trivial. Morally, this is the fact that if I take a generic automorphism of R and I raise it to any power, it's conjugate to itself. But that's not true for all automorphisms. There may be some special ones. So that's not how we prove this fact, but morally, that's what's going on. So the Adams operations are trivial, and using that the Adams operations are trivial and our understanding of the Grothendieck group, you can actually describe all Schur functors. Any Schur functor breaks up as a sum of wedge powers with some universal constants up here that don't depend on which representation you look at, but depend on which Schur functor you're looking at and which wedge power you're looking at. So there's some, so for example, sim squared breaks up as wedge squared plus v.
Does it depend on the characteristic of the field? The C mu I?
Should not depend on the characteristic, no. Yeah. The Grothendieck group, all of the rules, work over any characteristic, yeah. Okay.
And so are there any other categories for which which Adams operations are trivial? Simple.
Yeah, SN and ST. Are there any other? What other? No. Why are you shaking it? Oh, right, because those don't work.
Like the only example.
This is the only example.
That we know.
Right, because for SN, it stops working at N.
Well, Victor had this student, right, who proved that.
She's here and she will give a talk about it.
Oh, yeah, sorry.
Okay.
Yeah.
Please come to talk by Agustina.
Ah, great. Yeah. Good. Yeah, thanks. Sorry. Any other comments on that? Okay.
But SN, I mean, power of a permutation is not conjugate.
No, SN is
No. I was confused. I can explain. No,
It cannot be a finite.
I read something yesterday that confused me, and now I forgot everything I
ST,
knew.
yes?
Yeah. No.
This
It doesn't work. This is the only example.
That's the only example.
So is the direct sum from I equal to 0 to the length of mu, or can it go to more than that?
It should only be length of mu.
Or maybe size.
Yeah. Size of mu. Okay.
Use partitions.
Yeah.
Sorry, I meant size of mu. Yeah, not the number of rows, but the total box.
Yeah. Okay. So that's the end of the structure results. I'm almost out of time, but I don't have very many slides left. I want to explain why we call this the Delannoy category. So there's a model for these Hom spaces in terms of something called Delannoy paths, which are counted by something called Delannoy numbers. So maps from Rn to Rm have a basis indexed by n by m Delannoy paths. So a Delannoy path is a path that is allowed to go right, up, or both right and up. Okay? So this is an example of a 3x2 Delannoy path. So this is analogous to, you'll sometimes see ST called the partition category, and that's, somehow related nomenclature. So we're just calling this the Delannoy category because there's a basis indexed by n by m Delannoy paths, and it's easy to translate a path like this into some function. So what am I supposed to do? I have 3 input variables, which I'll call x's, and 2 output variables, which I'll call y's. And this picture is going to correspond to the characteristic function of the property x1 is smaller than x2 because I stepped in the x direction. Now I step in, this less than is, what am I doing? I understood how to do this when I was making the notes. Okay, so if it's equal, I'm doing the, definitely the last one should be x3. That is certainly true. Yeah, so that's right. So what I want to do is, in each spot, I put an x if I stepped right and a y if I stepped up, right? So to go from here to here, I stepped right, so the next thing that appears should be an x. Then I step both of them, the first one steps right, so that should be an x. The next one steps both of them, so I should put the next x and the next y. Then the next one goes up, so I should just put a y, and then the next one goes right, I should just put an x. That's the example. Okay? That's how you do the translation. And the interesting thing is the rule for composition is easy to describe in terms of Delannoy paths, which is that to compose one path with another, well, I need some signs that I don't want to get into, but it's a sum over 3-dimensional Delannoy paths whose projections in each of the 3 directions are P, Q, and R. Okay? So if I took a path like this, I can project on the xy direction and I will get this. I can project onto the yz direction and I will get that. And I can project onto the, this is the xz direction, that gives me this. This is the xy direction, that gives me that one. I get those 3 projections. And what this tells me is that this path assures for me that the composition of this with this contains that, which you can see here. Okay? And you can recover the same composition rules that we saw before by just looking at these projections of 3-dimensional paths. You might wonder whether you could completely describe perm G mu using paths. The tensor product rules are easy and the associator rule is easy. The thing that's annoying is tensoring morphisms. So the formula for tensoring morphisms is a little bit worse than anything that I wrote down, and so that is sort of the most annoying part if I wanted to give a purely elementary description of this category that never mentioned oligomorphic groups or anything. Okay. And then with my 0 minutes, I only have, I just wanted to say, we have another paper about the circle version of all of this. So you instead take your groups to be automorphisms of the circle with cyclic ordering. You again use Euler characteristic. Now the measure of the group is 0. So that's a bit of a problem. But the measure of all the open subgroups are not 0. So this is this quasi-regular case. And so you get an abelian category, but it's not semi-simple. And we say a lot of things about this category, but not as much as what we say about the line category because it's not semi-simple. So we classify the simples, projectives, and injectives. It's tame. So in fact, we classify the indecomposables. In fact, all but one block are semi-simple. There's one tame block. And that's what it looks like. We compute the branching rules. Now the branching rules go down to the Delannoy category rather than products with itself. We compute its semi-simplification. We have a version of Delannoy paths where we can give a combinatorial model, but there's also some stuff we don't know. In this case, we don't know the fusion rules. Well, what that means in a non-semi-simple case, we don't know how things break up when you take tensor product, and we assume that the characteristic of K is 0, and this is because if you take n points in the circle, there's a stabilizer coming from, or a normalizer. There's like that open subgroup is contained in another open subgroup where you take a semi-direct product by that Z mod n. And if the representation theory of Z mod n isn't semi-simple, then your life is harder. So probably you could go back and do a bunch of this stuff in characteristic P, but we did not try, and that's why. Okay.
So the non-semi-simple block is the principal block.
The non-semi, so the principal block meaning the one with the unit in it? Yeah, absolutely, yeah. And there, the simple objects are like wedge powers of L dot and L circle. Like, anyway, they're relatively contained. Yeah. All right, I will stop there.